Hello, so today we are talking about correlation of data. And so the correlation, if you think about two things being correlated, we're talking about how are they related to each other. So we have moved down to chapter 3, in your textbook. So this is section 3.1. We backtracked a little bit. So we are looking at the relationship between two quantitative variables. So we can only look at quantitative variables or numerical variables, meaning both of my axes need to be numbers in order to find a correlation. So bivariate data is just the study of two variables. We talked about this in class. And what we're looking at are, do some variables help explain or cause changes in the other? And we said the explanatory or the explain variable is my x variable, and the response is going to be my y. And we looked at this diagram in class and said the price of the lemonade is the response to the temperature, which is explaining the change. So we describe outliers or interpret outliers using FODS. So the first part of FODS is the form. What is the data, or what do the dots look like? Are they curved, linear/straight, or do they have no clear form? Sometimes they're just going to look like a hot mess and they have no clear form. Outliers talks about, is there one value or maybe two that just fall outside the overall pattern? And we gave an example of that if we think about data that looks like this. So if this is kind of linear up or linear positive, but we have a point like right here. This guy would be the outlier because he's away from the overall trend of the data. And there's no official rule for outliers. There's no 1.5 times IQR rule. It's just noticing, is there one point that's just really far from the overall trend of the data? Then direction, we talk about, is it positive or negative in direction? Is there a positive or negative association? And that brings us to strength, which talks about how closely do the points follow a linear pattern. Are they weak, moderate, or strong? These are my three descriptors that we use in statistics. So today we are going to focus on strength of a linear model. So we're going to focus on the S in FODS, the strength of a linear model. So correlation is the fancy word that we use to describe strength. So correlation is notated by an R. So if you see R equals, that's referring to the correlation. So correlation measures the direction and strength of linear data. It has to be linear in order to look at a correlation. So direction, if it's a positive number, then the data has a positive association. If R is a negative number, the data has a negative association. So you see some examples down here of different correlations in different graphs. So for example, negative 0.9, that's a pretty strong correlation, and you can see all the points are pretty close together. Whereas negative 0.5 is really weak, and the points are pretty far apart. This is an example of no real correlation. There's no trend in this data. It's just a big blob. A correlation of positive 1 means that the data is in a perfectly straight positive line. So positive numbers mean my data is increasing, and you can see the closer I get to 1, the more linear this data becomes. So for the first key point is, what does the correlation tell us? Well, correlation is what percent of the variation or the change in the response variable can be explained or attributed to the explanatory. So make sure you write this down. This is the AP exam template. On the AP exam, or on tests in this class, it may say, describe the correlation, or what does the correlation tell us in context of the problem? And this is the form or the format we're going to use. So correlation is going to be a decimal that we can convert to a percent. So this right here is R, or whatever the correlation is. That percent of the variation or the change, or we could say decrease or increase, so what percent of the increase or decrease in the response variable, or what percent or increase in y, the y-axis, can be explained by the x-axis, or by the change in the x-axis. So we're going to see some examples of this in this video and in class, but make sure you get this template down. This is just like a conclusion statement that we've been working with. We use this format every time we interpret the correlation. So here are some more examples of correlation and how we choose how we're going to describe it. If a correlation is more than 0.85, or if it's more than 85% of the change in y being explained by the change in x, we call that strong. So this is a strong and positive correlation because it's increasing and it's greater than 0.85. But if something's less than 0.6 or less than 60%, we call it a weak positive. It's weak because I have points kind of everywhere, but it's still positive because it's in that positive direction, and this number right here is positive. If anything's in between 0.85 and 0.6, we call that moderate. Or we could say moderately strong or moderately weak, the closer I am to these two numbers. The same thing is true on the negative side. Something has a strong negative correlation if it's less than negative 0.85 or more than 85% in the negative direction. So the closer I get to -1, the more accurate that line becomes, the more close my points are together. If I'm greater than 0.60, or if I'm less than 60% in the negative direction, if I'm a negative number close to 0, then it's a weak negative correlation. And once again, anything in between these, so something in the 0.7s, that would be moderate. So if I'm in between those values, I'm moderate. If I'm closer to -1, I'm more strong or stronger. If I'm less than -0.6, I'm weaker. If your correlation R is roughly between -0.4 and +0.4, so if it's around 0, then we say there's no correlation. It's just a bunch of points with no clear form. And that brings us to key point number 2. The correlation is a value between -1 and +1. It's always a decimal in between those two numbers. It's never bigger than 1. The closer R is to -1 or +1, the stronger the association. So examples of that are like if R equals 0.99 or R equals 0.87, those are strong. Or I should give the negatives. R is -0.92. Those are strong associations or strong correlations. But the closer I am to 0, so if R is like 0.33 or R is -0.41, those would be weaker. So let's take a look at an example and kind of how this would be asked in a problem. So it says each member of a statistics class ran a 40-yard sprint and then did a long jump with a running start. The table below shows the sprint time in seconds and the long jump distance in inches. So these are two quantitative variables. They're both numerical. The sprint time in seconds is going to be my x, and the long jump distance is going to be my y. So usually the x is the first variable we're given, and the y is the second. So part A says make a scatter plot of the data and describe the plot. So if I think about setting up a scatter plot, I have a title, track data. The y-axis is my long jump. I saw that the values went from 65 to 184, so I went up by 50s up to 200. For the sprint time, that's my x-axis, but the sprint times went from 5.05 to 7.25. So they were much more kind of condensed. So I set up my axis and I did a little break. So I started at 5 and I went to 7.5. Remember we talked about this. This helps us just kind of make our axes a little bit more user-friendly. And it helps me see the trend of the data better. So if I think about plotting these points, 5.41 is my x and 171 is my y. So I'd come over to 5.41 up to 171 and I'd do a point right there. 5.05 and 184 would be about there. 7.01 and 90 would be right there. And I'm just going to keep doing the dots and keep plotting this data. So now we can see the data all together. I have all of these points plotted, and you can see that they're in a negative trend, or they have a negative association, and it's pretty, moderate or moderately strong. The points are pretty lined up well. So if I had to describe it, the form, I would say is linear. Outliers, there are no apparent outliers. There's nothing kind of glaring, so I can just say no apparent outliers. An example of an outlier would be, this is a fake point that I'm drawing. If there was a point like down here, this would be an outlier, but there's nothing like that, so I'm just going to say no outliers. Direction, it's negative. And then the strength, just by looking at the graph, I'm going to say the strength is like moderately strong. Or moderate to strong, we could say. So this is my FODS, F-O-D-S. You want to do these in complete sentences or in a kind of more context if this was on a test or quiz. So key point number 3, correlation can only be found between two linear quantitative variables. So because I had two quantitative variables, I had an x and a y, my data was linear, so when I looked at the form, it was linear data, and my data were both numbers or numerical data. Now I can talk about correlation. Since these three things are met, I can now find what is the correlation, what is my R, and what does it mean. So categorical variables cannot have a correlation. That's a common multiple choice question or tricky question on an AP exam. Categorical variables can't have a correlation. So if we finish this example, part B says, suppose we know the correlation is negative 0.84. How strong is the data? Well, if we think about kind of those markers or those guidelines we gave, we said if R is less than negative 0.85, then it was strong. And if R was kind of in between negative 0.85 and negative 0.6, it was moderate. Since I'm really close to this, I'm going to say that the strength is moderately strong. Since this is saying 84%, it's moderately strong. It's really close to being quote unquote strong. So since these are just kind of templates, we can say it's moderately strong and combine those two. Now part C is that template. So it says explain the correlation in context of the problem. Well, correlation is 0.84 or negative 0.84 in this example. So if I think about putting that in that template format, I can say 84% of the decrease, since it was a negative association, so 84% of the decrease in my y. Well, what is my y? My y is the long jump distance. So 84% of the decrease in long jump distance can be explained or can be attributed to the what? To the increase in my sprint time, or to the change in my sprint time. So this is how I explain correlation in context, or I use that template. 84% of the change in my y, or of the decrease in my long jump distance, can be explained or attributed to the increase in my x's, or the increase in my sprint time. So that's a wrap. We use correlation to determine strength between two quantitative variables. Need to be quantitative. You need to have two of them. And correlation is the strength, and it gives direction because it can be positive or negative. The closer to zero, the weaker the strength. Once again, this is section 3.1 in your textbook. That's where you will find your homework problems and extra practice. Thanks, and I'll see you next time.